chemicals that enhance the inflammatory response. Inflammation is triggered when body tissues are injured. That could be due to trauma, heat, chemicals, infections. It's got a lot of benefits. It's very important. An good inflammatory response is necessary. Prevents the spread of damaging agents, disposes of cell debris and pathogen, helps to alert the adaptive immune system that things are going on, and very importantly, as we've touched on several times, it sets the stage for repair. There are four cardinal signs of an acute inflammation. They are redness, heat, swelling, and pain. And then some people are sometimes we use a fifth sign called impairment of function, and that helps to prevent movement. So the stages of inflammation include an inflammatory chemical release, vasodilation, increased vascular permeability, and mobilization of phagocytes. So the inflammatory chemical release are released into the extracellular fluid as soon as a cell gets injured. When tissues or cells get injured, they release chemicals. When immune cells or non-adaptive cells, first and second line of defense cells get in, they release chemicals. Histamine, released by mast cells, is a very important inflammatory mediator. Kinins, prostaglandins, cytokines, and complement, they all work to induce inflammation. They cause vasodilation, which gives us the redness. They make the capillaries leaky, which gives us the warmth and the swelling. And they bring phagocytes into the area. So histamine, kinins, prostaglandin, complement, and cytokines are very important to us. Cytokines we'll talk more about when we get to the specific immune response, and complements we'll talk about in a few moments. Vasodilation and increased vascular permeability cause hyperemia, which is congestion with blood, and that's where the heat and redness come from our cardinal signs. Increased capillary permeability causes an exudate. Exudate is fluid. That fluid contains clotting factors and antibodies to get into the tissue. That will lead to swelling, another cardinal sign, edema. And that also pushes on nerve endings, and those nerve endings send pain signals to the brain, giving us our fourth cardinal sign of inflammation. That pain can also result from toxins from the bacteria or other things produced by our own cells, prostaglandins and kinins. The benefit of edema is that surge of fluid in the tissue keeps things from spreading around, and it also delivers clotting proteins and complement to the area. Clotting factors form a trap around everything, set up a scaffold for repair, and we'll see what complement does here shortly. Mobilize phagocytes. The first line of defense for these phagocytes is neutrophils. They come in first. If they can't take care of everything, macrophages will follow them. If the inflammation is because of pathogens and not just injury, we will also activate complement, and that will bring in adaptive immune cells, B cells and T cells, that we'll get to in the next couple of sections. In order to get these cells from circulation into to the location of the injury, we have to mobilize them. And the first step of that is to do leukocytosis. That's the releasing of neutrophils from bone marrow and other places where they are stored, waiting for the chance to attack. And that happens in response to chemicals released called leukocytosis-inducing factors. Those neutrophils will then circulate in the blood circulation. And when they get close to an area, they will attach to cell adhesion molecules in a blood vessel in response to the other chemicals that are in high concentrations around there, causing them to move to the walls, the edges of those blood vessels. And that process is called margination. So margination is led by cell adhesion molecules, and then those marginating neutrophils will flatten themselves, crawl between the endothelial cells that are making up that blood vessel lining, and move into the interstitial spaces, so they'll leave the blood vessels and go into the tissues behind the blood vessels, and that process is called diapedesis. From there, they will follow chemical trails to the site of the injury, and that process is called chemotaxis, and it's positive chemotaxis because they are moving towards the chemicals that they are sniffing out. About 12 hours after they leave the bloodstream, monocytes transform into macrophages, and they are taking the spots of the neutrophils that are dying and cleaning up prior to the repair. So when we get an injury like this nail to the finger, the cells that are damaged and any pathogens that are on that nail cause the release of inflammatory chemicals that cause leukocytosis, the release of neutrophils from where they are stored. Those neutrophils make their way to near the site of injury and move to the edge of the blood vessel. They marginate, and from there, when they get really close, they do diapedesis. They crawl between two endothelial cells into the tissue behind it, and they follow chemical signals by chemotaxis until they get close to the area where the injury has occurred. And I won't walk you through this table, but it's in your book, 21.4, and it gives you a lot of information about tissue injuries and responses to them. So clinically, some homeostatic imbalances. Pus is a creamy yellow mixture of dead neutrophils, tissue cells, living and dead pathogens. That can become an abscess if collagen fibers are laid down, and that pus gets walled off into a small sac, and that may have to be surgically drained. Again, there are bacteria that have found ways around our body defenses, including tuberculosis, which resist digestion by macrophages, and then they are able to live inside those macrophages. They form intracellular parasites, and they can form growths in places that are called granulomas, and those are large and they can be very dangerous. Antimicrobial proteins are going to help the innate defenses by attacking microorganisms directly or hindering microorganisms' ability to reproduce. Most of the most important of the antimicrobial proteins, at least the ones we're going to cover, are the interferons and complement proteins. Interferons are a family of immune modulating proteins, so they have an effect on immune cells, effect on body defenses. And they are really mechanisms to warn other cells. Once a cell gets infected, it's going to produce interferons to let other cells know that it's happened. So cells infected with a virus are going to secrete interferons and let the neighboring cells know. The interferons get to neighboring cells. They stimulate the production of things that will block viral infections and even degrade viral RNA. So that cell that's infected has lost the battle, but it's warning its neighbors, and its neighbors are ready to gear up and protect themselves from the virus. They include type alpha and beta. These are the ones that work that way. Interferon alpha and interferon beta also work on activating natural killer cells. A different interferon, interferon gamma, is secreted by lymphocytes, those T and B cells we'll talk about later on, and they have widespread immune mobilizing effects, and it is very good at activating macrophages. Interferons activate natural killer cells and macrophages, so they indirectly fight cancer. And we use artificial interferons, or manufactured interferons, to treat things like hepatitis C, genital warts, and multiple sclerosis. So when a cell becomes infected with a virus, it gets into the cell, starts making transcription, makes copies of itself, and in this case, it would also activate the RNA for interferon. An interferon would be produced, and interferon would go to the neighboring cell, to an interferon receptor, and that interferon receptor would trigger the production of anti-RNA, antiviral proteins to be produced, so that that virus, once it's released from the first cell, will have a hard time getting into the second cell. Complement is another system. It's about 20 blood proteins circulating in the blood in an inactive form. It's going to sound very similar to the clotting cascade, and it uses a cascade to do its job. Proteins include C1 through C9, and then we have factor B, factor D, and factor P, along with a bunch of other regulatory proteins. This is a major line of defense for getting rid of foreign substances before the immune system can become activated. It enhances inflammation and directly destroys bacteria. It's very good for our innate defense, and it's necessary and helpful to our adaptive defenses. There are 3 different pathways that can activate this complement system. The first is called the classical pathway. Antibodies bind to invading organisms, then bind to complement components and activate them. It's called complement fixation. Once that initial complement proteins are activated, the cascade begins to trigger. The antibody one, though, requires that you already have antibodies. The next pathway is called the lecithin pathway. Lecithin are produced by the innate immune system to recognize foreign invaders. They are some of these pattern recognition molecules. So when lecithin binds to specific targets on foreign invaders, it can bind and activate complement. It can fix complement. And the third pathway is the alternative pathway, and this is activated spontaneously when complement factors bind directly to foreign invaders. We don't need any other proteins to attach them, so the lack of inhibitors on a microorganism surface allow the alternative pathway to occur. Each pathway involves the activation of proteins in an orderly sequence. Each step catalyzes the next step in a cascade fashion. Again, it's very similar to the clotting cascade that we went over. All 3 pathways converge on a molecule called C3, and C3 is cleaved into C3A and C3B. So when you split C3, initiating the common terminal pathway, that enhances inflammation, promotes phagocytosis, and can cause cell lysis. Cell lysis happens when C3b binds to the target cell, and that triggers the insertion of more complement proteins that are together referred to as the membrane attack complex. That MAC forms and stabilizes a hole in the membrane of the microbe, and that causes water to come in and the microbe to lyse or burst. C3b is also an opsonizing agent, so phagocytes like to grab a hold of C3b and eat whatever it's holding. C3a, the other piece that's released, and most of the other pieces that are released from complement proteins are going to amplify inflammation. They'll stimulate mast cells and basophils to release histamine. They will attract neutrophils and other inflammatory cells by positive chemotaxis. So we have the classical pathway, the lecithin pathway, the alternative pathway. They all merge to make an enzyme that cleaves C3 into C3b and C3a. C3b uses C5b, C6, C7, C8, and C9 to give you this membrane attack complex, which opens a hole in the target membrane. And the parts that are released are going to be used to increase vascular permeability, attract phagocytes and chemotaxis, and in general help the adaptive immune system get started. So a couple other things, fever. Fever is an abnormally high body temperature, systemic response. It goes throughout the entire body for invading organisms. Leukocytes and macrophages that are exposed to foreign substances secrete chemicals that we'll call pyrogens, and pyrogens act on our body's thermostat found in the hypothalamus and raise the body temperature. That causes the liver and the spleen to sequester iron and zinc, and iron and zinc turn out to be limiting factors for the growth of bacteria. So if you don't have enough iron or zinc, the bacteria cannot grow. In addition to that, that slight increase in temperature increases our metabolic rate and the way enzymes work and helps to increase the rate of repair. So moderate fevers are good. So we have phagocytes, natural killer cells, an inflammatory response, antimicrobial proteins, including interferons and complement, and fever.